All right, the nice part about this section is that there's not a lot of proofs. In fact, I wouldn't say there's really any proofs. What I would say is there's a little bit of factoring, similar to what we did in section 5.1. What we are now doing is going back to solving for x. Solving trig equations, which means knowing your unit circle is going to be extremely important. Your algebra techniques from Algebra 1, when you solved for x, we're going to be using those again. Those ideas of combining like terms, factoring, trying to isolate the trig function on one side of the variable. Just like when you solved for x, you always tried to get x alone on one side. Well, we're going to try to get a trig function alone on one side, and if we do it correctly, we will be able to solve for x. Here, similar to way back in algebra, if I gave you 2x plus 1 equals 0, you would add, if I gave you 2x minus 1 equals 0, I'm hoping you would solve that in your head. It's no different here. We're doing operations to both sides. The same operations you would do to 2x minus 1. 2 sine x equals 1, divide by 2, divide by 2. So the algebra, I hope, is not the hard part. You get sine x equals 1/2. Here's the tricky part. Now you got to know your unit circle really well. There are two places on the unit circle. The sine of what is equal to 1/2? And one of those being pi over 6. Okay, pi over 6 is in quadrant 1. There is also a value in quadrant 2. Another possible x value is 5 pi over 6. Now here's the tricky part. If you wrote just these two answers on a quiz, cannot give it full credit because they want all values of x. And anything coterminal with pi over 6 would also be a value that would make this statement true. So pi over 6 works, but technically wouldn't 13 pi over 6 work as well? Isn't that those two angles are coterminal? And anything coterminal with 5 pi over 6 also works. So I could say 17 pi over 6. And this could keep going, and I don't want to have to write all these angles up because it's never ending. So the way we are going to conclude our answers, right? Because, like I said, just what's written on the board right now, not enough. So the two ways we're going to say our answers, well, pi over 6 works, plus 2 pi k, and 5 pi over 6 plus 2 pi k, where k is an integer. Integers have to be whole numbers. So if I multiply by 1 or 2 or 3, that's like adding 1, 2, or 3 revolutions. And adding a revolution to pi over 6 is going to be a coterminal angle. So this would get us full credit. This is very good thinking, but not completely correct. So I want to pay attention. The first two problems, these directions are slightly different than these directions. And I look at this problem and I say, in algebra, there were times where you had x on both sides of the equation. And here we do. We have x on both sides of the equation. So what are you going to want to do? You're going to want to get x on one side of the equation. That's 2 sine x plus radical 2 equals 0. So subtract radical 2, subtract radical 2. 2 sine x. I go fast through the algebra because I'm assuming you know it, and that you can subtract both sides, an operation to both sides. And we end up with this statement of sine x equals negative radical 2 over 2. Happens in two places on the unit circle. Happens in quadrant 3 and it happens in quadrant 4. Now here, x equals in quadrant 3, that's 5 pi over 4. And in quadrant 4, 7 pi over 4. Now, the difference here is they only want the solutions on the unit circle between 0 and 2 pi. Everything else doesn't matter. So here I don't need to add the plus 2 pi k because I've listed all of the possible answers on the unit circle. Right, so it's a slight difference in directions. All right, so here, going back to one very similar to the first problem, solve for x, meaning get x values by itself. So again, the algebra involved I don't think is the hard part. All right, tangent squared x equals 1/3. I will say one of the most common errors I see in algebra, when you square root both sides, you get tangent x is equal to the square root of 1 over the square root of 3. And people think this is correct, but not really. When you take the square root of both sides, you need plus or minus. So here we have tangent x is equal to plus or minus 1 over radical 3. That happens on the unit circle. It actually happens 4 times on the unit circle, but the period of tangent is only is 1, so we can look at it in just quadrants 1 and 2. Another way to write this would be radical 3 over 3 plus or minus. So whichever one you're comfortable with, you have to know on the unit circle that happens, 4 times on the unit circle. Technically it happens at pi over 6. It also happens at 5 pi over 6. Now the next place it happens is at 7 pi over 6, and it also happens at 11 pi over 6. The plus or minus values, the positive or negative radical 3 over 3. Happens when sine's value is 1/2 and cosine's value is radical 3 over 2. That's why you're getting this reading here. Now, the part about sine that's important here is the period of sine is only 1 pi. So I actually don't need these two, because what's going to happen is I'm going to say, because I need to state all values, if you notice the change in the directions, I need to solve all values. I need plus, and what I'm going to say is pi times k, and here it's plus pi times k, where k is an integer, and if you notice, if k was equal to 1, if I add 1 pi to pi over 6, I get the 7 pi over 6 that was on the unit circle. So you don't need to repeat yourself. There are more than one way to state the correct answer. I've seen several people do it many different ways, but again, the book is only going to give one, and this is the way that the book would give it. So it's tricky because sometimes you're saying the same thing, and the book is saying it a different way, and it sounds like you have 2 different answers, but you're actually looking at the same answer, just phrased differently. All right, so we have this problem, cotangent x, cosine squared x equals 2 cotangent x, and it looks a little strange because it has both cotangents and cosines in it, but if I fall back on the principles I know of algebra, and I say, all right, x is on both sides, we'll start with the very standards of what you learned in your algebra class and get x on one side. All right? And in fact, so you're going to start to notice some similarities back to algebra. So all I'm doing is copying over. All right, and I notice, all right, I have 0 on one side. Well, one of the most common strategies of algebra when 0 is on one side is to factor out. And if I factor out, I have a GCF here, I could factor out cotangent x. It leaves me with cosine squared x minus 2 equals 0. Well, now I could use zero product property, set the first piece equal to 0, and set the second piece equal to 0. And now we can go from here. All right, so we think the cotangent of what is 0? If you think, well, cotangent had asymptotes at 0 and pi, and in the middle was one of those 5 important points. It passed right through 0, past that pi over 2. So one of the possible answers here is x could equal pi over 2. Again, cotangent has a period of pi, so I would say plus pi k. And that's going to be part of my answers. Over here, we'll be looking for more answers using my algebra, adding 2 to both sides. Next up would be taking the square root, and I would say the cosine of what is equal to plus or minus radical 2. And if you were to type in radical 2 into a calculator, this is approximately 1.41. Why do I bring that up? Because is it possible to take the cosine of something and get a value bigger than 1 or less than negative 1? No, cosine is always between 1 and negative 1. Remember our cosine curve, right? It always rotated, like the top right here was at 1, the bottom right here was at negative 1, so it can never hit a value of 1.41 up here, up there. So you are not going to be able to get any solutions from this part. Your only answers are right here. So when I look at this problem and I boil it down, I see a trinomial on the left-hand side set equal to 0. So I say, well, trinomials, and especially when one of them is squared and the middle term is, this looks like a trinomial to me, that I can factor. So I'm going to try to factor it using, like we have in previous sections. So I know I need a 2 sine x, and I need a sine x. I know one of these is going to have to be a minus 1, the other one's going to have to be a plus 1. And I know I factored correctly now. I can check that. That is completely correct. And now I could use zero product property, just like you have when you've solved for x in the past. The ZPP, as Mr. Marsh would call it. So 2 sine x equals negative 1. So I would divide by 2. So now I'm looking where is sine x equal to negative 1/2? Happens twice in the unit circle, which is actually the only two places I need to talk about here, because notice the change in directions. So where is sine negative? It happens at 7 pi over 6, and it also happens at 11 pi over 6. And then my other part of this is, if I add 1, go back to my second equation, where is sine x equal to 1? That only happens once on the unit circle, and it happens when x is equal to pi over 2. All right, so these problems get a little more difficult from here, and what I'd like to do is start with this problem in our notes when you come to class. So next time I see you, we will be taking a few more notes on problems like this, and one slightly more difficult, as well as some calculator work that could help you down the road. All right, see you then.